Before going into details about different converter topologies used for power conversion in PV systems, I will present a general overview of different system architectures. The architecture determines how PV modules are interconnected and how the interface with the grid is established. Which of these system architectures will be employed in a particular PV plant depends on many factors, such as the environment of the plant, whether the plant is situated in an urban environment or in an open area, scalability, costs, etc. In this video, we will discuss different architectures, focusing on the main advantages and disadvantages. Let's start with the simplest architectures employed in PV systems, the central inverters installation. Here we have that PV modules are connected in strings, leading to an increased system voltage, and then the strings are connected in parallel, forming a PV array, which is connected to one central inverter. This configuration is mostly employed in very large-scale PV power plants, with the central inverter usually being DC to three-phase and performing both maximum power point tracking and power conversion. In the case where more than one string is connected in parallel, and the significant differences in the irradiance from string to string are expected, blocking diodes are required to prevent current circulation inside strings. Concerning the inverter, many different topologies are used as three-phase inverters, and sometimes they are organized as a single DC to three-phase unit, but sometimes as a three-phase DC to AC single-phase units working with a phase displacement of 120 degrees each. Such a centralized configuration, having all the PV modules connected in a single array, offers the lowest specific cost, which is the cost per kilowatt peak of installed power. And finally, it is important to notice that this is a quite established architecture, which means it is reliable enough to work for a couple of decades. In spite of their simplicity and the low specific cost, central inverter systems suffer from some disadvantages. First, we have that due to the layout of the system, a large amount of power is carried over considerable distances using DC wiring. Therefore, the engineer has to be careful with the type and thickness of DC wires, because this can cause safety issues related to fault DC currents. So, special precautions must be taken, such as thicker insulation on the DC cabling and special circuit breakers, which can increase costs. Another drawback is that all strings operate at the same maximum power point, which could be problematic in a very large installation. Imagine, for example, a cloud casting its shadow on part of the installation for a couple of seconds. The result is a high imbalance in power generation throughout the modules that causes mismatch losses and reduces the overall system output. Third drawback is the low flexibility and the expandability of the system, because the central inverter is designed to work with a specific installed peak power, and hence it will not be able to handle more and more input power. Therefore, the system design is difficult to extend and not very flexible. Lastly, since we have to use blocking diodes in each string to prevent current circulation, then we have to consider also their additional power loss. A very different architecture is that of the module inverters, also called microinverters, because it is just as big as the junction box. These inverters operate directly at one or several PV modules and have power ratings of several hundreds of watts. Because of the low voltage rating of the PV module, these inverters often require a two-stage power conversion. So in the first stage, the DC voltage is boosted to the required value, and then it is inverted to AC in the second stage. The output voltage has to be compatible to the grid, to which they are connected by means of an AC bus, and in order to avoid any imbalance on the phase, all the microinverters are connected together with a special additional unit, depending on the brand, which controls the output signals of each inverter. As I mentioned, microinverters are very small, and this is because inside they have a high-frequency transformer, which decreases the cost and space occupancy with respect to the main transformer. Additionally, it provides a full galvanic isolation, which enhances the system flexibility and makes this concept easily expandable. So, for example, if after a couple of years we want to install more modules, we can just buy an additional number of microinverters and a new power unit that controls all of them. Let's now see the drawbacks of such a system, because all these advantages came at a price. Since these inverters are mounted on the backside of a PV module, their embodiment has to be very sturdy in order to operate in a harsh environment such as high temperature and large daily and seasonal temperature variations. Again, special attention should be posed on safety issues related to cabling to avoid that animals bite the cables, resulting in conduction failures. Another disadvantage is that the PV module voltage is much lower than the output AC voltage. Therefore, the DC-DC conversion has to boost considerably the voltage, and this has a detrimental effect on the inverter efficiency. Also, if you have a very large number of modules, then it is no longer economically interesting because the specific costs are the highest of all the inverter topologies. Similarly to the previous case, the topology based on the power optimizers relies on operations at single module level. It is especially flexible for roofs in urban environment and expandable to a certain extent. Power output is optimized by offering maximum power point tracking at the module level, and the installation is simplified because of the DC bus topology. Passing to the drawbacks, also this topology needs a sturdy embodiment for the power optimizers to be mounted and operated safely at the back of each module. In addition, newer bifacial modules which promise higher current levels may not be handled by the current involved electronics. This topology is suitable for a small system in the range up to 10 modules. After that, limitations on voltage and specific costs become too stringent for this topology to perform well and be also economically viable. The fourth architecture features string inverters, which combine the advantages of central and module integrated concepts with the little trade-offs. So here modules are connected in series to form a string, like for the central inverter concept, with a power rating of up to 5-6 kilowatt peak in one-phase configuration, and the open circuit voltages are up to 1 kilovolts, which already makes one disadvantage of this topology apparent. Indeed, high DC voltages require special consideration, as in the case of central inverter architecture. Here, this issue is even more important because string inverters are usually being installed in households or on office buildings without designated support structures or increased safety requirements. The protection of the PV system also requires a special consideration with emphasis on proper DC cabling. Another important characteristic is that if each string has its own maximum power point trigger, then each string can independently operate at its maximum power point. Thus, partial shading and hotspots will occur only in modules inside the string because of unequal current and power sharing. Also, because no strings are connected in parallel, there is no need for blocking diodes as in the case of central inverter, and as a consequence, the losses associated with these diodes are reduced. The multi-string inverters architectures is a hybrid between a central and the string inverters topology. Here, an optimizer box is attached to every string, and it contains a maximum power point trigger and a DC-DC converter. The DC to AC conversion instead is shifted to a power electronic unit just next to the grid. So all the string optimizer boxes are connected in series to each other and then to the central inverter. It is important to note that if the DC input voltage of the central inverter is outside the specific input range, then current is altered such that the voltage falls within the acceptable range again. So the main advantages of this architecture is that every string can operate at its maximum power point, and the optimizers operate at voltages close to the voltage of the string. Hence, the DC-DC conversion is very efficient, and the optimizers consume very little power. In this architecture, we can easily add additional strings, but not only you have to be careful that the inverter can handle the additional power input, but you have to also buy an additional DC-DC converter, which is a drawback. Finally, based on the string concept, we have the team inverters configuration suitable for places with variable meteorological conditions. Basically, it is a combination of several string inverters working with the team concept to reduce the overall losses as any power electronic converter is designed such that it has maximum efficiency near full load. The concept of team inverter is that each string is connected to a bus that is activated or not, depending on the amount of power that the PV modules are generating. So, at very low irradiation, the complete PV array is connected to a single inverter, while with increasing solar irradiation, more inverters are being connected, dividing the PV array into smaller units until every string inverter operates close to its rated power. In this mode, every string operates independently with its own maximum power point tracker. Of course, with this master-slave fashion, we need to have an additional intelligent circuit that basically makes a round robin in the usage of all these inverters in order to not always use the same one. To sum up, in this video we have seen 6 main installation concepts for solar inverters. The first and easiest architecture is the central inverter, which connects in parallel different strings directly to one single 3-phase inverter. The second type we have been through features module inverters. Here, some microinverters are directly connected to one or a few PV panels. As we have seen, this design makes the system more flexible and easy to expand. On the other hand, the cost can become prohibitive if there is a high number of modules. Similar considerations hold for the topology based on power optimizers. Next, we had a look at a system concept which utilizes string inverters. In this case, each string of panels in series is connected to one single inverter, and then several inverters are connected in parallel between them. The fifth architecture is the multi-string inverter one. In this case, each string of PV panels is connected to a DC-DC converter that adapts the voltage level to meet the requirements of a single central inverter. Here, the DC to DC converters are all in parallel. The last concept we have seen in the video involves team inverters. What happens in this case is that each string is connected to a bus, activated or not, depending on the power intake from the PV modules. As we said, we need an additional intelligent control to apply this architecture, which translates into more complexity. It is important to say that each of the presented concepts is valid, but it has to be accurately chosen depending on the system project and cost.